Ma'am, is it revision by session, ma'am?
Once again, I'm not able to hear you clearly. What is it?
Revision by session.
This session is on chemical reaction engineering too.
Huh, I think it's revision or not.
Revision session. Yeah, it's a kind of a summary session.
Okay.
Okay. So
Okay.
I welcome you all for the week 12 live interactive session for the course chemical reaction engineering 2. Okay. Let's get on to the session. So this session will be a summary session where we'll have brief recap of all the week's lectures, and then we'll also solve some problems covering all the major topics. Okay, so you're able to see my screen, Kirtana.
Yes, ma'am.
You're able to hear me also, right?
Yes, ma'am.
Okay, okay. Now let's get on to the session. So we'll have the brief recap of all the week's lecture. So let's start from week one. So week one had a brief introduction on the course, and then the catalytic reaction was introduced, where introduction to catalysis and catalytic reactors, history of catalytic reaction and role in economy, and classification of catalytic reaction like homogeneous and heterogeneous catalytic reactions were discussed. And then what are the properties of catalyst, especially the surface area, and examples of certain catalyst, what are supported and unsupported catalyst. Do you remember what is a supported catalyst? Can you just cite an example? Do you remember anything in catalytic reaction? Okay, let me say an example. It is like something like platinum supported on alumina. You would have seen like PT slash Al2O3, right? Kirtana, are you there? Okay. I think we lost the connection of Kirtana. So that is one of the example of a supported catalyst. And then how does a catalyst work? uh, you know what is an adsorption on the catalyst side, what are the active sites, and then classification of catalyst based on class of reaction and the catalyst used were discussed. Seven steps of catalysis, which involves two external mass transfers. One is the reactant external mass transfer into the entrance of the catalyst pore, and then the other external mass transfer involves movement of the products from the catalyst pore to the bulk. And similarly to internal mass transfer, where the reactants entering inside the pore, and similarly the products coming out of the pore. And then adsorption of reactants, reaction, and then desorption of the products. These are the seven steps of catalysis. So what is the rate equation for external and internal diffusion control? And what is an adsorption isotherm, and what is a non-dissociated or molecular adsorption, what is a dissociated adsorption, especially the Langmuir adsorption isotherm was discussed in week 1 lecture. Week 2 lecture involved the surface reaction term. What happens when there is a single site or dual site mechanism, and then Illy-Riddle mechanism, and then single site rate equation, and dual site uh, mechanisms, especially the Langmuir-Hinshelwood kinetics, where there is one adsorbed species or two adsorbed species, or dual catalyst two adsorbed species was discussed, and then Illy-Riddle mechanism was discussed, and a desorption step. So, how does the rate law looks for a desorption step was discussed, and what happens to the rate law when the surface reaction is rate limiting, and two examples were discussed on forming the rate law. One is on ammonia synthesis, where nitrogen adsorption is the rate limiting, and the other one is carbon monoxide with nitrous oxide, where the surface reaction is rate limiting. And then how do you synthesize the rate law? Postulate the mechanism, decide the rate controlling step, find the rate law, validate the rate law with the experimental data. So there an example problem of cumene to benzene and propylene was discussed under this, where there was an assumption of Langmuir-Hinshelwood kinetic mechanism, with adsorption as rate limiting, surface reaction as rate limiting, and desorption as rate limiting. How under each of these cases the rate law was covered. And then what happens when one of the steps in catalytic reaction is irreversible. So a pseudo steady state hypothesis for the species would be assumed. So that was discussed, and with an example. And then what happens when there's a temperature dependence? And then how do you steps involved for reducing the rate law, finding the mechanism, finding the rate parameters, and designing a reactor was discussed with the example of hydro demethylation of toluene. And finally, the week 2 lecture involved a design of reactor, especially of the packed bed reactor. And week 3 lecture included discussion on design of packed bed and CSTR reactors, and then a case study of chemical vapor deposition with surface reaction as rate limiting. And catalyst deactivation was introduced in week 3 lectures, where the types of kinetics, rate law, catalyst decay rate, decay mechanism, sintering and aging, aging process, which is one of the catalyst decay mechanism, was discussed. And then further, the decay law for sintering, and then isomerization in batch reactor with catalytic deactivation was discussed. What happens when there is a coking and fouling or catalytic poisoning process were all discussed among in catalyst deactivation. And what if catalyst poison is there in the feed, and if the poisoning is by reactant or product is itself, and what are the various decay law were all discussed in week 3. Week 4 lecture, it had some continuation on catalytic deactivation, where fluidized CSTR design was discussed, and then choice of reactor. What happens when there is a slow decay and moderate decay? So, what would be the choice of reactor? What was discussed, and then as catalysis process involves the diffusion steps, so the effects, diffusional effects were introduced, and the concept of effective diffusivity and internal diffusion effects. The model development for internal diffusion effects was discussed, and non-dimensionalization of the model. And then the concept of Thiele modulus was introduced, and how does the concentration profile look, and then internal effectiveness factor, concept of internal effectiveness factor were all discussed in week 4. Week 5 had continuation on internal effectiveness factor, where the expressions for a spherical catalyst for first order and nth order reaction, and then for a slab core catalyst, and when there is a volume change in the reaction, so how does the internal effectiveness factor the expression changes, and what if the reaction is exothermic or endothermic, and what happens when there is a multiple steady state were all discussed, and falsification of kinetics was discussed, and then external mass transport limitation was introduced in week 5. So Kirtana, are you there? Okay. So week 6 had detailed discussion on when the external mass transport is limiting in a catalytic reaction. Mass transfer coefficient for a single particle without reaction, where Frost-Link correlation was introduced, and then mass transfer coefficient for a single particle with reaction, where surface reaction is rapid and diffusion is relatively faster. And then packed bed reactor design with external mass transfer limitation was discussed, where length correlation between length, superficial velocity, area of contact, mass transport coefficient, and conversion. The expression for each and the correlation for each were explained. And then Theonos-Kramer correlation, Coleman correlation were discussed on packed bed reactors. And then an example problem was solved where the mass transport coefficient for a packed bed reactor was estimated using both Theonos-Kramer and Coleman correlation. Uh, was uh, was done. Uh, week 7 included discussion on overall effectiveness factor, where both the external and internal mass transfer resistances are comparable. The Weiss-Prater criterion was introduced to identify the internal, uh, uh, or internal diffusion control regime or reaction limited control regime, and then Mears criterion to identify if there is a external mass transfer control, and then packed bed reactor design and then expression for its conversion was discussed, and then what are the limitations of Weiss-Prater criterion, and then the need for a generalized framework with example reaction was discussed, and what is the generalized criterion was also covered. Week 8 included when n species are participating in a first order reaction, what are the vector forms and matrix notations, and how do you use the experimental data to identify if it is an external mass transfer limiting or internal mass transfer limiting or surface reaction limiting was all discussed. And then the packed bed reactor design with internal and external resistances were discussed. The design equation for first order and second order reactions were covered. And then the fluidized bed reactor was introduced in week 8. What are the advantages of fluidized bed reactor? What are the different fluidization regimes? In the Cooney-Levenspale model, what are its features? Factors affecting the FBR design, and then minimum and maximum fluidization velocity, the assumptions of Cooney-Levenspale model, and then gas velocity in immersion phase and bubble velocity were all covered. And then week 9 lecture uh, included discussion on fluidized bed reactor and also fluid solid non-catalytic reaction. In under fluidized bed reactor, the Morivend correlation and Werther correlation for bubble diameter, solid velocity, expression for solid velocity, and then material balance on gas flow and mass transport in a fluidized bed reactor. And then the mass transfer in a fluidized bed reactor between the bubble and cloud, and then cloud and emulsion, and the reaction in a fluidized bed reactor where the expression for a first order reaction, the expression for height at a desired conversion time and weight of catalyst for that desired conversion were were discussed. And then the fluid solid non-catalytic reaction was introduced. So what are the types of products and models and examples of each of the reaction for each model? What is the progressive conversion model and what is the shrinking core model? What are the assumptions involved and how does the concentration profile look in each of these cases? And what are the different rate control mechanisms and expressions for a shrinking core model when the gas film is controlling the reaction, and then an ash layer controlling the reaction. What is the expression for the time and the time for a complete conversion were all discussed. Week 10 lectures included further continuation on fluid solid non-catalytic reaction, where discussion on when reaction is rate controlling for a shrinking core model where the particle size does not change, and also when particle size changes, what is an expression for when the reaction is rate controlling and when film diffusion is rate controlling were discussed. And expression for T by tau for a spherical particle, flat plate, cylindrical particle was discussed. And then an example problem was also solved on dissolution of solid particles when the particles are monodisperse and polydisperse. And week 10 also initiated discussion on residence time distribution. It introduced the non-ideality, where and how the non-ideality happens in a reactor, and then the distribution of residence time in a gas liquid reactor and packed bed reactor, and CSTR, the concepts of identifying non-ideality in reactor, and real world reactors design approach, and then RTD for ideal PFR, ideal batch reactor, and uh, and stir tank reactor was discussed. And measurement, how do you measure the resistance time distribution? So what is a tracer, what are the characteristics of tracer, what are the injection methods for a tracer, step and pulse input were all discussed. So, week 11 lecture included discussion on RTD, where the C curve, RTD function, and its limitation for a pulse input and step input were discussed. And then, what are the E curve and the F curve, and what are the other tracer technique? What are the mean residence time, variance, skewness, normalized RTD function, what is an internal age distribution, and then RTD in ideal reactors like PFR, single CSTR, and a laminar flow reactor was discussed. And then RTD for diagnostics and troubleshooting was discussed in week 11. And then the week 12 lecture, the final week lecture included the reactor diagnostics and troubleshooting, where CSTR and PFR combination with PFR with normal and bypassing and dead volume. How does the RTD function look like when the PFR and CSTR is under ideal condition, and when it has some bypassing and dead volume? And what happens when PFR and CSTR are in series? What is the RTD and what is the performance? So is RTD alone enough for to estimate the performance, or what other information do we need, like on mixing? Micro mixing and macro mixing, the concept of globule, macro and microfluid were discussed. And then the zero parameter model, segregation model, and maximum mixedness model were all discussed in the week 12 lecture. And this covered the entire chemical reaction engineering 2 concepts. Now let's get on to the practice assignment session for the week 12. Question number 1. An elementary irreversible liquid phase reaction 2P giving Q, where the rate constant K is equal to 2 liter per mole per minute, takes place in an isothermal non-ideal reactor. The E curve in a tracer experiment is shown in figure. Pure P of concentration 2 mole per liter is fed to the reactor. Using segregated model, the percentage of conversion of P at the exit of the reactor is dash. We have to find out what is the percentage conversion of the reactant P. So this is a GATE question which was asked in GATE 2022. Now let's and this is what is the E curve that was given. So now let's see how to solve this problem. So given it's P gives Q, which is an elementary reaction. That means elementary reaction means, so we have to just directly take based on the rate expression will be based on the stoichiometry. So that means it's a second order. So 2P gives Q. That means it is second order with respect to P, the reactant P. That means the rate expression is minus Rp is equal to K into Cp square. Right? Now next. They've also given the reaction rate constant is 2 liter per mole per minute, and the initial concentration of P, where pure reactant is fed, and the concentration of the reactant P is 2 mole per liter. Now E curve is shown in the figure. We have an E curve of this shape. Okay. Now we have to find find what is the average conversion using a segregated model. Right. So first we have to find out what is the function for function for the E of t. What is the RTD function? So in order to find RTD function, first of all we know that f of t is equal to integral 0 to infinity E of t dt is equal to 1. So this area under this E curve is going to be 1. Right? So this can be further written as integral 0 to infinity E of t dt is equal to, if you look into this figure, so this entire figure can be split into two parts. One is a rectangle up to this. right? And then a triangle. So it is the area of rectangle plus area of triangle. So we know that this point they have given it as 1, right? And this point is 0.5. That means the x and y value of this point is 0 comma 1, and here it is 5.5 comma 0, and here it is 0.5 comma 1. Whereas here we know the value of x, which is 0.5, but we do not know what is the y coordinate at this point, right? So in order to find out that, we are approaching so this figure by calculating the area under the entire curve. Okay, so the entire curve can be split as a rectangle and a triangle. So this is the rectangular portion and this is the triangle portion. So it is the area of rectangle plus area of triangle. And we know that the total value is equal to 1. Because integral 0 to infinity e of t dt is equal to 1. So that means which is equal to area of rectangle can be found out, right? Base into height. So it is 0.5 into 1 plus area of triangle, it is half into base into height. Half into base is 0.5 again, and height we do not know. Sorry, this is actually height we do not know. We do not know the height. So we have all the other terms. So with the values of all the other terms, we can find out that h, the value of h, the height of this triangle, this portion is 2. That means the value of y will be this plus this, right? Because it is here. That means this 1 plus 2. That is 1 plus h, that is 1 plus 2, that is y is equal to 3. So the coordinates of this point are 0.5 comma 3. Now we have found out what are the coordinates of this point. Now we have to find out what is the expression of e of t. So if you look into the curve of e of t, we can find that it is a straight line between the points 0 comma 1 and 0.5 comma 3, right? So what is an expression equation of a straight line? It is y is equal to mx plus c. So here it is e of t is equal to mt plus c, right? C is nothing but the intercept. The intercept value is 1, right? So c is 1. And then what is the slope? So slope between these points, it is 3 minus 1, that is y2 minus y1 by x2 minus x1. So it is 3 minus 1 divided by 0.5 minus 0, that is equal to 4, right? So once we substitute those values in the e of t expression, we will find that the expression for the residence time distribution, the e curve is 4t plus 1, right? Now the next step is segregated model for finding the average conversion for a second order reaction. So the expression is 1 minus xa bar is equal to Ca bar by Ca naught, that is equal to integral 0 to infinity Ca by Ca naught. So in segregated model, each element of the fluid can be considered as a single batch reactor or a little batch reactor of age t into its its residence time, that is E of t dt, residence time distribution E of t dt. Alright, so for a second order reaction, Ca by Ca naught is equal to 1 by 1 plus K into Ca naught into T. So substituting that expression of Ca by Ca naught into the average conversion expression, so we get 1 minus xa bar is equal to Ca bar by Ca naught is equal to integral 0 to infinity 1 by 1 plus K into Ca naught into T multiplied by E of t dt, right? So here when we look into the time, it is just it's not from 0 to time t equal to infinity, but it is between time 0 to 0.5, right? After which the curve goes to 0. That means the time is from 0 to minute to 0.5 minutes as we observe in the E curve. Right. So, uh, substituting the values of k and ca naught into the expression and then the value of time also in the integral limits, you will get 1 minus xa bar is equal to ca bar by ca naught, that is equal to integral 0 to 0.5 1 by 1 plus 2 into 2 into t, the whole multiplied by e of t dt. E of t is 1 plus 4t into dt. So if we look at, you will get 1 by 1 plus 4t multiplied by 1 plus 4t into dt. So you cancel both. So you will end up with 1 minus xa bar is equal to integral 0 to 0.5 dt. Right? So integration of dt is nothing but t. And applying the limits of 0 to 0.5, you will get an expression for 1 minus xa bar is equal to 0.5. That means xa bar is 0.5. So this implies that the average conversion for this, residence time distribution curve for this particular reaction is 50% based on the segregated model. Question number 2. This is again a GATE question which is asked in GATE 2017. For a solid catalyzed gas phase reversible reaction, which of the following statement is always true? So adsorption is rate limiting, desorption is rate limiting, solid catalyst does not affect equilibrium conversion, temperature does not affect equilibrium conversion. Which of the following is true? So let's see which of the following is true. So can adsorption rate limiting be always true for a solid catalyzed gas phase reaction, reversible reaction? No. Similarly, desorption can also not be always true because the reaction can be either adsorption limiting or desorption limiting. Similarly, temperature definitely affects the conversion. Right? So what is the only statement that is true is that the solid catalyst does not affect the equilibrium conversion. So your equilibrium conversion is not affected by the presence of catalyst. Right? It only changes the kinetics, not the equilibrium conversion. Okay. Now let's get on to question number 3. This is again asked in GATE 2020. The square of Thiele modulus MT is given by MT square is equal to L square into K, where L is the characteristic length of a catalyst pellet, K is the rate constant of a first order reaction, order reaction, and D effective is the effective diffusivity of the species in the pore. So MT square is a measure of, so MT square is it a measure of time scale of pore diffusion by time scale of reaction, or is it a measure of rate of pore diffusion by rate of reaction, or is it a measure of time scale of reaction by time scale of pore diffusion, or is it a measure of rate of reaction by rate of mass transfer? So which of these is true? So looking into the expression, L square into K by D effective is equal to MT square. So the answer is it is the MT square is a measure of, or in other words, the Thiele modulus is a measure of time scale of pore diffusion by time scale of reaction. So how do we understand this? From the definition of Thiele modulus gives the ratio of MT square, or it is phi n square is equal to surface reaction rate by diffusion rate. Okay. So if we look into the definition of each of these terms, a rate of a quantity measures change in some quantity per unit time. So it has a unit of time in the denominator. So from the definition of Thiele modulus, the surface reaction rate is moles of A reacted by time of reaction, and diffusion rate is moles of A diffused by time of reaction. So Thiele modulus is mole of A by time of reaction, mole of A reacted by time of reaction whole divided by mole of A diffused by time of reaction. In other words, this can also be expressed as mole of A reacted into time of diffusion by mole of A diffused into time of reaction. That means if you just look into the time terms, it is nothing but the measure of time scale of pore diffusion to the time scale of reaction. So that is how it is. Mt square or phi n square or Thiele modulus is a measure of time scale of pore diffusion to the time scale of reaction. Okay. Now let's get on to question number 4. So this question is again asked, is a gate question. Okay, this it is asked in GATE 2017. The C curve measured during a pulse tracer experiment is shown below. Okay, in the figure, C of t is the concentration of the tracer measured at the reactor exit in moles per liter at time t seconds. Now we have to find out what is the mean residence time in the reactor, rounded off to 1 decimal place in seconds. Okay. So how do we approach this? So the mean residence time is given by integral 0 to infinity t into c of t dt by integral 0 to infinity c of t dt. So integral 0 to infinity c of t dt is nothing but the denominator in the expression is nothing but the area under the curve. So area under this curve we have to determine. So here the area under the curve is nothing but the area under the triangle. So area under the triangle is half into base into height. So the base is the value is 2 and the height is 1. That means half into 2 into 1, that is equal to 1. So integral 0 to infinity c of t dt is equal to 1. Now we have to find out the expression for the numerator, that is integral 0 to infinity t into c of t dt. So if we look into the curve, this curve can be split into two straight lines. One is starting from 0, 0 to 1, 1, and then the other straight line is from 1, 1 to 2, 0. Right. So we can rewrite the expression for integral 0 to infinity t into c of t dt as integral 0 to 1 t into c of t dt plus integral 1 to 2 t into c of t dt. Now in order to find out what is the expression for c of t in the region 0 to 1. So it is nothing but a straight line from 0, 0 to 1, 1. So the expression for straight line is y is equal to mx plus c. Here it is c of t is equal to mt plus c. So here the intercept c is equal to 0 and slope is 1 minus 0, y2 minus y1 by x2 minus x1. So 1 minus 0 by 1 minus 0. Right. So that means that is nothing but 1. So you end up with the expression of c of t as is equal to t for the region 0 less than t less than 1. Between 0 to 1, the value of c of t, the expression for c of t is t. Now, the expression for sorry, I missed a part. Sorry, I missed a part. So when you look into the other part of the curve, where you have integral 2 to 1, here again it is going to be a straight line equation with the so we can write the expression and you will end up with an expression for that as 2 minus t. Okay, so integral so you have two expressions where uh, you will end up with two expressions. So one of the expression for 0 to 1 is c of t is t and the other expression from 1 to 2 is c of t is equal to 2 minus t. So substituting both the expression into the expression of integral 0 to infinity t into c of t dt, you will get integral 0 to 1 t into dt plus integral 1 to 2 t into 2 minus t into dt. So so that is equal to integral 0 to 1 t square into dt plus integral 1 to 2 2t minus t square into dt, right? And then the integration of t square is t cube by 3. Similarly, integration of t is nothing but t square, t square by 2. So substituting the integration values and then applying the limits, you will end up with the expression for integral 0 to t t into c of t dt is equal to 1, right? And finally, the uh, the mean residence time is equal to integral 0 to infinity t into c of t dt divided by integral 0 to infinity c of t dt. So for the expression for the value for integral 0 to infinity t into c of t dt is 1. That is what we determined. Similarly, for integral 0 to infinity c of t into dt is also the expression is 1, right? So your mean residence time is it's actually not 1 minute, it is actually 1 second, because the time units given in the question is seconds, t seconds. Okay, sorry for that mistake as well. Okay, the mean residence time is 1 second, it's not minute. Okay, now question number 5. This is again a gate question. A vapor phase catalytic reaction where Q plus R gives S follows Riedel mechanism. R and S are not adsorbed. Initially, the mixture contains only the reactants in the equimolar ratio. The surface reaction step is rate controlling. With the constants A and B, the initial rate of reaction minus R naught in terms of total pressure PT is given by, so is it expression A minus R naught is equal to A into PT by 1 plus B into PT, or is it uh, is it B minus R naught is equal to A into PT by 1 plus B into PT square, or is it C minus R naught is equal to A into PT square by 1 plus B into PT, or is it D minus R naught is equal to A into PT square by 1 plus B into A into PT square divided by 1 plus B into PT the whole square. So which of these is the right? So let's proceed with the solution. So they have given the reaction follows Illy-Riddle kinetics with surface reaction controlling, right? And the species R and S are not getting adsorbed. The reactant R and similarly the product S are not adsorbed. So what will be the mechanism? So it will be Q is getting adsorbed. So V is the vacant site. So Q plus V gives an intermediate Q dot V, and R plus Q dot V gives S plus V, because R and S are not getting adsorbed. Okay. The step A is a reversible and step B is an irreversible reaction. Okay. Now we have to find out what is the expression for the overall reaction rate especially at the initial condition. Okay. So Q plus V gives QV. So this is a fast step because the surface reaction is what is controlling. That means the adsorption step is very fast. So rate of adsorption is equal to K, the the adsorption coefficient into PQ, that is the pressure of the reactant Q, partial pressure of reactant Q into CV minus CQV by KQ, right? That so that is equal to 0 because this this step is going to be very fast, right? So the rate of adsorption is equal to 0, right? So you will get CQV is equal to KQ into PQ into CV. Okay, and then what is an expression for the total concentration of the active sites? So C total is equal to CV plus CQV. So vacant site plus the adsorbed sites. So from the previous expression based on the adsorption of Q, we can substitute the value expression for the CQV, which is an intermediate. So that will give you CV is equal to CV plus KQ into PQ into CV. So CV is equal to CT by 1 plus KQ into PQ. So the surface reaction is rate controlling. So R plus Q dot V gives S plus V is the rate controlling step. So the surface reaction rate is equal to Ks into CQV into PR. This is especially we are writing only for this portion because they have asked only for the initial where the product concentrations are zero, right? And we have assumed based on that we have assumed an irreversible reaction. So that means Ks into uh, CQV into PR, whether PR is a partial pressure of R, right? So substituting that, you will get Ks into so substituting the value for CQV, you will get Ks into KQ into PQ into CV into PR is the expression. Now substituting for CV in terms of the total active sites concentration, you will end up with an expression where minus R naught dash is equal to Ks into KQ into CT into PQ into PR by 1 plus KQ into PQ. Given equimolar concentration of Q and R. So PQ is equal to PR is equal to PT, let's assume. Okay. So also Ks into KQ into CT is equal to A and KQ is equal to B. You will end up with minus R naught is equal to Rs is equal to A into PT square by 1 plus B into PT. So the solution is option C. So the option C in the given expression is minus R naught is equal to A into PT square by 1 plus B into PT. Okay. Now let's get on to question number 6. Nitric oxide plays an important role in smog formation and there are great incentives for reducing its concentration in the atmosphere. It is proposed to reduce the concentration of nitric oxide in an effluent stream from a plant by passing it through a packed bed of spherical porous carbonaceous solid pellets. A 2% nitric oxide and 98% R mixture flows at the rate of 1 into 10 power minus 6 meter cube per second. That is nothing but 0.001 decimeter cube per second through a 2-inch internal diameter tube packed with porous solid pellets at a temperature of 1173 Kelvin and a pressure of 101.3 kilopascal. The reaction is given by NO plus C gives CO plus half N2. It is the first order reaction with respect to NO. So the reaction rate is given by minus R dash R prime is R prime of N naught is equal to K1 double prime into SA into concentration of nitric oxide, and occurs primarily in the pores inside the pellet where this internal surface area SA is given by 530 meter square per second and the specific reaction rate constant in terms of the surface area K1 double prime is 4.42 into 10 power minus 10 meter cube per meter square second, and then K prime K1 prime in terms of the weight of the catalyst is given by K1 double prime into SA, that is equal to 4.42 into 10 power minus 10 into 530. Okay, that will give you 2.34 into 10 power minus 7 meter cube per gram second. And then the bulk density of the catalyst bed is 1.4 into 10 power 6 gram per meter cube. And also K1 in terms of the the K1 is K1 prime, sorry, K1 is K1 prime. So multiplying the bulk density of the uh, catalyst bed. So you will get K1 is equal to K1 prime into rho B. So you will end up with the value of 0.328 second inverse. They also given additional information like at 1173 Kelvin, the fluid properties are The kinematic viscosity is 1.53 into 10 power minus 8 meter square per second. Effective diffusivity is 1.82 into 10 power minus 8 meter square per second. And gas diffusivity is 2 into 10 power minus 8 meter square per second. The properties of catalyst and the bed are also given, where the density of the catalyst particle is 2.8 into 10 power 6 gram per meter cube. The bed porosity is 0.5. The bulk density of the catalyst bed is 1.4 into 10 power 6 gram per meter cube. The radius of the catalyst pellet is 3 into 10 power minus 3 meter, and the sphericity of the catalyst pellet is 1. That means it's a spherical catalyst. Okay. So, for the given data, the reaction was found to be both internal and external mass transfer limiting, and the weight of the catalyst required was estimated to be 455 grams. Now, we have to estimate the following if the particle size is reduced by a factor of 2. What are the parameters we have to find out? We have to find out the Weiss-Prater parameter CWP, and then identify if the reaction is internal mass transfer limiting even when the particle size is reduced by 2, factor of 2. And we also have to find out where the Mears parameter for external diffusion limited, and find out if the reaction is external mass transfer limited also. And finally, we have to calculate the catalyst, the weight of the solid porous catalyst necessary to reduce the nitric oxide concentration of 0.004 percent. That means the final concentration of the nitric oxide should be 0.004%, which is below the Environmental Protection Agency's limit. Okay, this is how the schematic. So the nitric oxide entering, the concentration of nitric oxide entering is 2%, and the nitric oxide coming out is 0.004%. Okay, now we have to start with the solution. Now they have given that we have solved a very similar problem in week 6 for the original radius of 3 into 10 power minus 3 meter. Meter. Now here in this case, we have to see what happens when the radius is reduced by a factor of 2. That means the radius is halved. So the radius of the pellet is reduced by a factor of 2. So R is equal to, so 3 into 10 power minus 3 by 2, that is 1.53 into 10 power minus 3 meter. Sorry, I missed the unit here. It's meter. Okay. Initial concentration of nitric oxide they have given us 2%. Final concentration is 0.004%. That means we can find out what is the conversion. The conversion is 2 minus 0.004 by 2. That is CAB naught minus CAB by CAB naught. So you will end up with a conversion of 99.8%. Now what is the Weiss-Prater parameter? Weiss-Prater parameter is given by the eta into phi 1 square, where eta is the internal effectiveness factor and phi 1 square is the square of the Thiele modulus. So that is equal to 3 into phi 1 into cot h phi 1 minus 1 for the case of first order reaction. And they have also given that the reaction is first order with respect to nitric oxide. Now, what is the expression for Thiele modulus for a first order reaction? So, phi 1 is equal to R into square root of K1 double prime SA into rho C by dE. So, we have all the values, right? We have the value of radius, we have the value of K1 double prime, we have the SA value also, right? Surface area is 530, which is given, rho C is also given, right? Catalyst density is given, and the effective diffusivity is also given. So substituting all the values, we will end up with the value of phi 1 equal to 9. So very high Thiele modulus. This is a higher Thiele modulus. Right. So where if you substitute this Thiele modulus value in this cottage expression, you will get the value as 1 only. So your eta can be simply written as 3 by phi 1. That is 3 by 9. That is 0.333. Okay. Now so Weiss-Prater parameter is eta into CWP is eta into phi 1 square. So that is eta is 3 by 9 into 9 square. Phi 1 is 9, so 9 square. So you will end up with the value of, sorry, 3 into 9. Yes. Okay. So 3 into 9, that is 21, 27. So this value of 27 is very much greater than 1. That means if the waste parameter is very much greater than 1, then it is definitely an internal mass transfer limiting reaction. So even though the catalyst particle size has reduced by half, it is still an internal mass transfer limiting reaction. Now part 2 is finding out the Mears parameter to identify if the external mass transfer is limiting. So Mears parameter is given by minus RA observed into rho B bulk density of the catalyst bed into R into N, where N is the order of the reaction, by Kc into CAB. Okay. So R observed can be written as omega, that is overall effectiveness factor into minus RAB. Okay. So substituting and the expressions for minus RAB also, you will get Mears parameter is omega into K1 prime into CAB into rho B into R into N is 1. So and that can also be included. So you will get R divided by Kc into CAB. So CAB gets cancelled. So your Mears parameter is omega into K1 prime into rho B into R by Kc. Now the unknowns in the above expression are the overall effectiveness factor omega and the mass transport coefficient Kc. Now let us look into the expression for overall effectiveness factor. Overall effectiveness factor omega is given by eta divided by 1 plus eta into K1 double prime into SA into rho B by Kc into AC. So if you look into the expression for overall effectiveness factor, here again we have to the unknown is your mass transfer coefficient Kc. So in order to estimate the Mears parameter and also the overall effectiveness factor, first we have to estimate what is the value of Kc, which is nothing but the mass transport coefficient. So for finding out mass transport coefficient, it's a packed bed reactor, we can use the Thiemann-Kramer correlation. So Thiemann-Kramer correlation is given by modified Sherwood number is equal to 1 into modified Reynolds number power 0.5 into Schmidt number power 1 by 3. So your Schmidt number is your kinematic viscosity divided by the mass diffusivity DAB. So nu, the value is given as 1.53 into 10 power minus 8 meter square per second. DAB is also given, the diffusion coefficient 2 into 10 power minus 8. So you will end up with the Schmidt number to be 0.765. And then Reynolds number, the modified Reynolds number is Reynolds number divided by 1 minus phi, where phi is the porosity of the bed into gamma, where gamma is nothing but your sphericity. Sphericity here is 1. Okay. And from here we need what is the value of Reynolds number. Reynolds number can be written as the superficial velocity into the diameter of the particle divided by the kinematic viscosity. So diameter of the particle is here it is 3 into 10 power minus 3 meter. Superficial velocity can be given by volumetric flow rate by area of cross section of the bed or the tube. So volumetric flow rate they have given, it is 1 into 10 power minus 6 meter cube per second volumetric flow rate. And area of cross section of the reactor or pipe, they have given the diameter of the so it is AC is equal to pi d square by 4. So the diameter of the pipe is given, which is nothing but a 2-inch diameter. Alright. So substituting the value, you will get the area of cross section of the bed is 2.03 into 10 power minus 3 meter square. Superficial velocity can be found out from these two values. So it is 1 into 10 power minus 6 divided by 2 into 2.03 into 10 power minus 3. You will end up with the value of 4.93 into 10 power minus 4 meter per second. So from this you can find out what is the Reynolds number value. So you have the value of U, dP and mu. So 4.93 into 10 power minus 4 multiplied by 3 into 10 power minus 3 divided by 1.53 into 10 power minus 8, you will get the Reynolds number to be 96.65. And from here the modified Reynolds number can be found out. The porosity of the bed is given 0.5 and gamma sphericity is equal to 1. So you will get the modified Reynolds number to be 193.3. And then Sherwood number. So the Sherwood number, modified Sherwood number is 1 into Reynolds number per modified Reynolds number power 0.5 and Schmidt number power 1 by 3. So substituting the value, you will get Sherwood number approximately equal to 13. Sorry, modified Sherwood number to be equal to 13. So from this, the mass transport coefficient is modified Sherwood number into uh, you know diffusion coefficient divided by diameter of the particle into 1 minus 5 by 5 into gamma. So substituting the value of all, you will get the mass transport coefficient to be equal to 8.6 into 10 power minus 5 meter square per second. Now, we should also find out what is the external area per unit volume of the reactor AC. That is given by 6 into 1 minus 5 divided by dP. So, phi is the porosity of the bed and dP is the diameter of the particle. So, we have all the values. Phi is equal to 0.5 and dP is 3 into 10 power minus 3. So, you will get AC is equal to 1000 meter square per meter cube. So we have the value of mass transport coefficient, we have the value of AC. Now we can find out what is the overall effectiveness factor. So overall effectiveness factor is given by eta divided by 1 plus eta into K1 double prime SA into rho B by Kc into AC. Now we have the values of all the terms. So you will end up with eta equal to overall effectiveness factor to be 0.15. So we have the mass transfer coefficient and also the overall effectiveness factor. Now we can find out the Mears parameter. So substituting the expression for Mears parameter is omega into K1 prime into rho B into R divided by Kc. So substituting all the values, you will get your Mears parameter to be 0.86. So if the Mears parameter is greater than 0.15, then external mass transport limitation exists. So here again, in this case of reduction of the particle size by a factor of 2 also, your external mass transport limitation exists. So from this it can be inferred that both internal and external mass transport limitation exists for this particular reaction and they are the limiting factors for the reaction. Okay. Now we have to calculate what is the weight of the porous catalyst. So conversion, we know that the initial and final concentration of the nitric oxide, from this you got the conversion to be 0.998. Conversion at the exit of the reactor is, the expression is given by x is equal to 1 minus exponential of minus omega into k1 double prime into SA into rho B into L by U. Okay. So this can also be rewritten as 1 minus exponential of minus omega into k1 into L by U, where L is the length of the reactor. U is the superficial velocity, omega is the overall effectiveness factor, and k1 is the specific reaction rate constant. So where N is the length of the total length of the reactor. So substituting all other parameters, we just want to find out what is L. So you will end up with the value of L to be 0.062 meters. Okay. Now from this, weight of the catalyst required can be calculated. So the weight of the catalyst required is W is equal to rho B into AC into L. Right. So density of the bed into the area of cross section of the bed into the length of the bed. That will give you what is the weight of the catalyst required. So it is 1.46. So rho B we know 1.46 into 10 power 6, and AC we know 2.03 into 10 power minus 3, and L we just found out it to be 0.062. So where W is we get as 176.2 gram. So initially when the particle diameter was 3 millimeter, the weight of the catalyst required was 455 grams. While when the particle diameter reduced by half, the weight of the catalyst required becomes 176.2. That means there is a 61% reduction in the weight of the catalyst required when the particle size reduced by a factor of 2. Okay. But So based on these calculations, so should we go ahead with the reduced particle size, or should we go ahead with the initial particle size, which was 3 mm, or should we go for a reduced particle size of 1.5 mm, r equal to 1.5 mm? So this actually depends not only on the weight of the catalyst, which is reduced by 61%, but also the cost involved in reducing the particle size from uh, you know a 3 mm to 1.5 mm. So uh, the actual selection of the catalyst will depend on the cost of that catalyst with the reduced particle size, and also the the original size and the weight used in each of these cases. So based on that, you know a, an optimum value will be obtained. Okay, now let's go on to the final question for the session. Spherical particles of zinc blende of size R is equal to 1 millimeter are roasted in an 8% oxygen stream at 900 degrees C and 1 bar. The stoichiometry of the reaction is 2ZnS plus 3O2 gives 2ZnO plus 2SO2. Assuming the reaction proceeds by shrinking core model, calculate the time needed for complete conversion of the particle. Okay, they have also given additional data like density of solid rho B is equal to 4.13 gram per centimeter cube, that is equal to point. That is equal to 0.0425 mole per centimeter cube, and then the reaction rate constant K double prime is equal to 2 centimeter per second. For gases in the ZNO layer, the effective diffusivity is 0.08 centimeter square per second. They have also given an additional information that the film resistance can be safely neglected as long as a growing ash layer is present. Okay, now let's proceed to see how this question is to be solved. So given uh, you know the zinc blende, zinc sulfide is roasted. Okay, and this is following a shrinking core model. So that means sulfide ore roasting with a shrinking core model, it happens without overall particle size shrinking. That means there will be a presence of ash layer and the overall particle size will be maintained as r equal to 1. Only thing is that the ash layer thickness keeps on increasing. Okay, now they have also given the film resistance is negligible. Now what are the resistances for the reaction now remaining? One is the ash layer resistance and the other one is the reaction resistance. Okay, so the overall time for complete conversion will be tau total is equal to the time for tau of ash layer plus tau of reaction. So for a spherical particle, tau of ash layer is rho b into r square divided by 6b into d into cag, where rho b is the density of the particle, r is the radius of the particle. Okay, b is the stoichiometric coefficient, and de is the effective diffusivity, and cag is the gas concentration. And tau, sorry, it is actually tau of tau reaction. Okay, tau of reaction is rho b into r divided by b into k double prime into cag. Okay, now So your value of B will be 2 by 3. How is it 2 by 3? In the sense, we start with the expression, DNA by A is equal to DNB by B, right? That means where A is a gas and B is the solid. So uh, so it is DNA. Here the gas is oxygen. So DNA by 3 is equal to DNB by 2. Right? That means DNB is equal to change in moles of B. That is a solid is, it is B by A into DNA. So that is why you get the value of B is equal to 2 by 3. So that is dividing this whole expression by 3. That is the stoichiometric coefficient of oxygen. You will get the coefficient of zinc blend ZNS is 2 by 3. Okay. Now we have to find the concentration of oxygen. So the concentration of oxygen they have given as it is a 8% oxygen stream. So assuming that the percentage given is mole percent, now we have to find out the CAG, that is the concentration in terms of concentration terms, right? Because they have given it in terms of mole percent. Okay. So CAG at standard temperature and pressure, that is 273 Kelvin, and 1 bar is N by V, right? So N is a mole percent, so 8 by 100 divided by V, where V is a volume occupied by 1 mole of gas at STP, which is nothing but equal to 22,400 centimeter cube. So substituting this, you will get the CAG at standard temperature and pressure is 3.57 into 10 power minus 6 mole per centimeter cube. Okay, but here we cannot use this value directly because they have given the temperature of the reaction is 900 degrees centigrade, which is nothing but 1173 Kelvin. So assuming the pressure does not change and the pressure is, they have also given in the question that the pressure is at 1 bar and right. Okay, so P is equal to 1 bar. So for ideal gas law, P is equal to CRT, where C is the concentration. Right, substituting this in the expression and rewriting it, you will get concentration of the gas at 273 Kelvin divided by concentration of the gas at 1173 Kelvin is equal to T2 by T1, where T2 is the temperature 2, that is 1173 Kelvin, and T1 is the temperature 1, that is the standard temperature 273 Kelvin. So substituting the values, we have the concentration at 273 Kelvin. We know the value of T2 and T1. So you will get concentration at 1173 Kelvin is 8.31 into 10 power minus 7 mole per centimeter cube. Now we have to substitute the all the values in the tau of ash layer. So tau of ash layer is equal to rho B into R square by 6B into DE into CAG. We have all the values. We have also calculated what is CAG, what is B. So it will be 0.0425 into 0.1, because the radius they have given it as 1 millimeter, that is nothing but 0.1 centimeter. All are in terms of CGS units. That is why we have substitute as 0.1 centimeter. A square divided by 6 into 2 by 3 into 0.08, and the value of effective diffusivity into CAG is 8.31 into 10 power minus 7. So we'll end up with tau ash as 1598.2 second. And similarly, your tau of reaction. Sorry. So similarly, we can find out what is the value of tau of reaction. Right. So the tau of reaction is it is rho B into R by B into K double prime into CAG. We also have all the values, so we will end up with 3835.7 seconds. So the total time for complete conversion is tau ash plus tau reaction, that is equal to 1598 plus 3835, that is equal to 5433.9 seconds, which is approximately 1.5 hours. So the time taken for total conversion of the zinc blend of 1 mm 1 mm radius with 8% of oxygen flow is 1.5 hours. Okay, so this is what is the expression. Just before concluding, so this expression can also be, this reactions rate step, reaction step can also be written as a reversible reaction. Okay, where the, and then they have asked only the expression for initial reaction rate. So the reversible part of that reaction, that is when you write it as a reversible reaction, you will get Rs is equal to Ks into CQV into PR minus 1 by K of S into concentration of S into concentration of the vacant site, right? So since they have asked only the initial expression for the initial reaction rate, the reverse term will become zero, as there is no as there is no S initially. So they have mentioned that it is equimolar concentration and only the reactants are present initially in the reaction. Okay, and you will again end up with the same expression. Okay, but that expression will be applicable only for that initial rate, not for the entire spectrum. But if you assume it as an irreversible step, then for the entire spectrum, this will be the expression for the reaction rate. Okay, so that's it with the session. All the best for your exams. In case you have any doubts, in case you have any doubts, uh, you can just mention in the forum.